We got our test coming up tomorrow. It covers Think Well chapters 3 and 4, and we'll go through topic by topic here. Chapter 1 is actually what's called Math Fun. We didn't do anything yet in that. We may do something in Chapter 1 by the end of the semester. Chapter 2 was just a review of Calc 1, so... But Chapter 3, we took a look at L'Hopital's rule. L'Hopital. And being able to calculate a limit. But the limit must be in a special form before we can use L'Hopital's rule on it. What form, what indeterminate form or forms does it work on? Okay, 0 over 0 or infinity over infinity. Now, we did take a look at a lot of limits. Many of them were already in this form, but then there were some by the end of the homework that we had other indeterminate forms, and we had to change the form algebraically into either infinity over infinity or 0 over 0. But basic idea, if it's in these forms, then all we need to do is take the derivative of the top, derivative of the bottom, recalculate with the limit. If we again get 0 over 0 or infinity over infinity, we do another set of derivatives. Now notice this is not the quotient rule. Okay, it's just the derivative of the top function is the new top function. Derivative of the bottom function is the new bottom function. And then you probably have some algebra to do to rewrite and see, do we need to run through L'Hopital's rule again, or can we just plug in the number and get the limit? Sometimes it just takes once, sometimes it takes 3 or 4 times through L'Hopital's rule before we get an actual value. Okay, so any questions on just the basic ones where we already have the infinity over infinity or 0 over 0? Now some of the other forms that we had to change, infinity minus infinity, 0 to the infinity, 1 to the infinity, infinity to the 0, and several others we looked at, and we had some different procedures. A lot of times the infinity minus infinity were 2 fractions that we had to combine and make it one, do the algebra, get common denominators, and then go from there. Now these last ones were more in the logarithmic form, or we needed to put them in logarithmic form. And for instance, if we had something like this as, well, let's go the other direction. Something like that, okay, and we had this as x approaches 0. Well, that would be 0 to the 0, another form there. How would we work through that one?
Put L in front of it. Set
Okay.
y, it's like L and y equals L and time.
Right. Now, the way I approach this is different from the way Professor Berger approached it. at least the beginning of it. The results are the same. But what I would do is say, let y equal this sine x to the x, and then take the natural log of both sides. Now for some of you this would work better, and then we pull the x out in front. Okay. Now others of you liked what Professor Berger did with, instead of changing the entire equation, he just said, well, this sine of x to the x, change that to e to the natural log of this inside. And then, well, what I do, what he did, we get the natural log of that original function. He just has it already in the exponent of e. What I do, figure out the limit, then remember to go back and take e to that power to get your limit. So either direction is fine. Either direction you'll end up with working with this right here, which as x approaches 0, we'd end up with 0 times, well, actually infinity, or negative infinity technically. So we would still, that's another one of those forms, indeterminate forms, that we have to rearrange the form of it. And usually when we have an x times something, we can make that the something divided by 1 over x, creates the fraction. So let's see what happens when we do that. We've got our natural log of sine x. We'll leave in the numerator, and then the x turns into the 1 over x in the denominator. And again, we're looking at this x approaching 0. I guess technically, for this to be absolutely correct, we'd have to have x approaching 0 from the right, because the natural log of some very, very small number only works if it's a positive. Okay. Little technicality there, but we'll work through that. So now we can take, we've got infinity over infinity, or actually negative infinity over positive infinity. L'Hopital's rule applies, and we can look at it as derivative of this, 1 over the inside times the derivative of the inside, and then derivative of the denominator. Well, this you'll have to think of as x to the negative 1. Derivative would be negative 1 x to the negative 2. And let's see. We'd have cosine x over sine x all over 1 over x squared, negative 1 over x squared, which we would then need to invert and multiply our denominator. We'd have x squared cosine x over sine x. Don't lose the negative sign, negative 1. And as, I guess, we're still looking at x approaching 0 from the right, what's this give us? This one turned out to be a little longer than I'd hoped, but we still have the 0 over, well, yeah, 0 over 0. 0 here, sine of 0 would be 0. So we can do one more time. And yeah, we got a little bit longer here than I'd wanted. I'm going to leave the -1 out in front. Derivative of x squared times cosine x, product rule on it. Derivative of the first times the second. So we'll have that in the numerator and cosine x in the denominator. Okay. So now, do we still end up with an indeterminate form? Okay, no. Nice to know this cosine x, cosine of 0 is 1, so we won't have the indeterminate form. What do we end up with, though? Okay, plug 0 in for x, and we'll get 0 in the numerator. So 0 over 1. Now, what I did, changing it to natural log of y, that this is saying natural log of y approaches 0 as x approaches 0. Or what we would see with Professor Berger, he'd have e raised to all of this. So he'd automatically go to e to the 0, which is 1. 1 is your answer. If you go with my direction, here we'd have to say y would be, change the natural log into your exponential form, e to the 0, which again is 1. So, slightly different approach, but should get you to the same answer either direction. Okay? And with L'Hopital's rule, that's probably the most complicated part of it when you have those 0 to the infinity or 0 to the 0, 1 to the infinity, something like that. It gets rather interesting. You got to change to your natural log somehow and work through that. So we took quite a while on the L'Hopital's rule. So there will be several L'Hopital's rules on the test. And in fact, there will be 20 problems on the test. That was all of Chapter 3 that we covered on the Think Well material. Chapter 4, we got into dealing with some more complicated functions, inverse functions. And the first couple of sections were more the generalization of inverse functions. I'm not going to have anything on those particular, or those general things. He went through the proof of how to get a derivative of an inverse function without knowing the inverse function, but we won't have anything like that on the test. What I'm more concerned with is, can you find the derivatives of the specific derivatives, the specific functions? Find the derivative, find the derivatives of the specific inverse functions. Now, we have kind of finished up with the inverse trig functions and introduced hyperbolic functions, but at the very beginning we started with logarithmic functions, logs of a different base than e. Okay, so log functions, and just in general, so you remember, hopefully you remember, what's the derivative of the log x base 2? One over, turns out to be the natural log of 2 times the x. So derivative of the natural log of x is just 1 over x. Derivative of any other base, it's still 1 over x, but in the denominator we'll also have the natural log of the original base. And we looked at the log properties as well, how to use the log properties to make finding the derivative so much easier. Okay. Something like this. If we want to find the derivative, well, I'm not going to start out looking at the derivative as the first step. There's lots of log properties here, and change the log form, then do the derivative. Very first thing we hopefully will notice, what can we do to the inside? Okay, we can raise it to the half power. Then that half power, the exponent, can go out in front. And we just made the derivative a whole lot easier. So we'll have the log of this fraction. Well, what can we do with the log of a fraction? Okay. Take the log of the top minus the log of the bottom. Now careful, this 1/2 is times all of it. So top of the next page, I'll try to remember what all I wrote. We'll have that 1/2 times the log of the numerator minus the log of the denominator. And this is still the original function, but in a much easier form to take the derivative of. Now, as we take the derivative, well, we'll have the 1/2 still be part of the derivative answer, and then the log of 3x plus 1 base 5, derivative there. Base 5, we got to change to natural log of 5 in the denominator. 1 over the inside, and then what? Okay, times the derivative of the inside. Okay, then the next one. And we're done, or once in a while there might be some little algebra you can do, but do not try to put this back into a single fraction. I know the answer key that the book has, it goes way beyond what you need to do. So this would be fine. If there is a little bit of simplifying within our fractions, and especially multiplying by the derivative of the inside, do the little things, but don't worry about the big things. That's just way too much to do. This is calculus, not algebra, so I want to see that you know the calculus part. Hopefully you also know the algebra, but I'm testing your ability to do the calculus. Now, beyond our derivatives of logs of different bases, the next thing we looked at was logarithmic differentiation, which uses log properties, but the basic problem there is we have no choice. Let's see, earlier we looked at this as a limit, but now let's look at this as a function. How would we find the derivative of this? Well, we've got to change it to a logarithm. and we can call that y. Natural log of y, x times the natural log of sine x. And now we're in the form that we can take the derivative. Now we are looking at natural log of y, so we have to use implicit differentiation. But we would just have 1 over y times the derivative of the inside, well, derivative of y with respect to x. And then the other side is our product rule. First times the derivative of the second. Plus the second times the derivative of the first. Well, put the derivative of the first, and then times the second. So the procedure is very straightforward once we get the exponent, the variable, out of the exponent. And then we've got to do one more thing, and try to fit it up here. We're solving for dy by dx, but we have the 1 over y times the dy by dx. What do we need to do to finish this out?
Multiply by y.
Okay, multiply both sides by y, so we'd have y times, well, all of this. And again, there's a little bit of simplifying you could do with this, but I'm not real concerned. Trig functions, there's all kinds of trig identities you could rewrite. There's probably 50 different ways you could write this answer. I would rather just have you write one easy way, not worry about the algebra and the trig identities to get there. So,
Could you have solved the other one just like that? And just left it at
the other one, the logs with the different bases, or are you saying L'Hopital's rule? Well, with L'Hopital's rule, we had to take the limit, and we had to get it in the form either 0 over 0 or infinity over infinity.
You could have put sine
So,
of the x on bottom and just left the x on top, couldn't you?
no. This is what we were looking at for L'Hopital's rule. So to get it in that 0 over 0 or infinity over infinity, we had to rewrite it. But if we're just looking for the derivative of this entire function, this is when we have to kind of use the logarithmic differentiation. Now, another log differentiation that I will say you must use logarithmic differentiation is something that we wouldn't necessarily need to with an a variable in the exponent, but some ugly big function that it would take the chain rule several times to get through. Say if we have a function something like this, cube root of this big old nasty fraction. Well, using logarithmic differentiation, we can make this a lot simpler. Before we worry about the derivative, and take the log of both sides. And then, well, we could, once again, the cube root, we could raise that to the 1/3 power and pull that out in front. And then we would have x plus 1 quantity squared over 3x minus 2. Once again, a fraction that we can separate out. Okay. And then there's also one more thing we could do here. This exponent could come out in front of just that one part. The 1/3 will be multiplied by both parts, but the 2 will only be multiplied by this first part. Okay. And, well, that's still just f of x. Now we are not f of x, natural log of f of x, natural log of y. Now we take the derivative, and again we got to remember the derivative of natural log of y is what we're looking at, and it's 1 over y times dy by dx, and then all of this, derivative of that. We've got a much easier derivative to calculate, and in fact derivative of the inside of that one's just 1, and then 1 over 3x minus 2 times the derivative of that inside. And now at this point we're not quite done. Remember, it's the 1 over y times dy by dx. So dy by dx will be, you got to take all of this times the y, the original y, which is that cube root. So since we're running out of space there, I'll stop there. I think you can follow that. But there will be a problem that I say, here's a function, use logarithmic differentiation to find the derivative. I'm not going to let you just go through the chain rule on this original one. You got to do the logs and all the properties. So, but I think it will, if you know those properties, it's a lot easier to do the derivative this direction. Okay. Now we did look at some inverse trig values, evaluating inverse trig functions, the 5.6 homework, but I'm not going to have any problems particular to that, but within some of the derivatives and integrals, maybe not in this chapter, but later on we'll need to be remembering that those concepts, and we'll kind of take that step a little farther in. I think it's the next unit we'll look at. But for this test, inverse trig functions, we looked at finding the derivatives and then turning around and finding the antiderivatives of those forms. So antiderivatives or integrals, the 5-6, 5-7 combination assignment, and a lot of that is just having the formulas. I'm not going to make you learn the formulas, memorize the formulas. I will allow you to have one sheet of notes, 8.5 by 11, front and back. Should be plenty of room, but that will be some of the main things you'll need on it. And then section 5.8, we talked about the hyperbolic functions. And again, with those, I'm not going to focus on the algebraic manipulation, but the derivatives. We only looked at derivatives on those. Later on, we might expand on the integrals, that form of the integrals, but at this point we only looked at the derivatives there. So the derivative of hyperbolic sine of x, well, that's something you'll need to have written down on your sheet. But that's pretty much the entire test. You've got calculating limits using L'Hopital's rule. You've got find the derivatives, lots and lots of different forms of finding the derivatives, but that's going to be another type of problem. And then find the integrals, and that was basically just your inverse trig functions as the answer, the integral of the fraction you're given. So to kind of, there are 20 problems. Each problem will be worth 5 points. You are allowed one sheet of paper. Both sides if you think you need that much space. And like I said, what you'll need on there, the many derivative formulas that we run into. Even if you need to do the logarithms and the log properties, you can put that on there. Some of you had asked about the inverse or the trig table to evaluate trig functions. Well, you could put that on there, but there's not going to be anything in particular on trig values.
You won't need the trig table?
Right. You wouldn't need the trig table, at least this time. Later on, we may be using it, but again, I'm more interested in can you find derivatives rather than can you evaluate trig functions. And then the last little bit from those, I guess more or less the inverse trig functions, from those derivatives we've created integral formulas. So the integral of the fraction that ended up being the derivative of, say, arcsine or arctangent, the integral of that. Okay, make sure you can work backwards there. So definitely the main things you should have on your sheet of paper, all those formulas. If you need to write down some examples of how to do something, that's fine. You can put anything you want to on that sheet of paper. Put "Oh Lord, help me" if you need to.
Great.
So, any questions?